So we're going to start chapter 15. Chapter 15 is all about taking integrals. So if you need to review the integrals and those materials that you learned in Calculus 1B, I highly encourage you to get back to 1B, take a look at your notes, go over the examples and practice a little bit. I also posted the integrals definitions and a cheat sheet for you on Canvas, so you have access to all sorts of integrals in this class. Perfect. 15.1, 15.2. So 15.1 and 15.2 are talking about taking the integrals over any other format for a two-dimensional space or a three-dimensional space objects. In Calculus 1B, you learned how to take the integral over a line or along a curve. In this chapter, we learned that if you have a surface, how do you take the integral over that surface? Instead of having integral just over along an inner wall or a curve, here you have a surface. The nicest format, nicest surface that you have is the product of two inner walls. So A, B, so A, B, multiplied by C, D. Second inner wall. The intersection between these two forms a two-dimensional object or just a plane, and your goal is to find the integral over this two-dimensional plane. We have iterated integral in chapter 15. Later on, you learn how to take the integral when you're working with volume. So officially, to define the double integrals, a to b, then c to d of a function like f of x and y with respect to two variables. Again, take a look at this shape. You have x-axis and you have y-axis. The first interval is defined on x-axis. The second interval is defined on y-axis. So you're taking the integral with respect to variable x, also with respect to variable y. We have to include both of them then to take the integral. So as you can see, you can separate the integral by taking the integral with respect to one of the variables. Note that interval c to d is on y-axis. So you can take the integral with respect to variable y. You either have a function or a number. Then you take the outside integral with respect to the second variable, which in this case is x. Iterated integral, which in this case is double integrals. Very well. If you switch these two intervals, a to b, c to d, you have to switch the order in which you take the integral. So the inside integral is now with respect to x, because AB is on x-axis. The outside integral is with respect to variable y, because y has interval c to d. Let's take a look at examples to feel more comfortable about this double integral. First example says, find double integrals. Y ranges between 1 to 2 and x ranges between 0 to 3 of function x squared times y. Very well. So let us take the integral, the inside integral, which is integral with respect to y. This is your inside integral. Very well. Inside integral is with respect to variable y. So the integral of y dy is a half y squared. Since it has x squared next to it, you copy down x squared as well. Your y ranges between 1 to 2. So first, we plug in 2 for y. We get x squared, 2 squared divided by 2, minus. Then we plug in 1 for y. X squared, 1 squared divided by 2. Then we start simplifying the rest of it. 4 over 2 minus 1 over 2, 3 halves x squared. We're not done yet. We just calculated the inside integral. Now you have to work with the outside integral, which is with respect to variable x. We found that the inside integral is 3 halves x squared. So this inside integral is nothing but a quadratic function, 3 halves x squared. Now we take the integral 3 halves x squared with respect to x. We have 3 halves x squared dx, which is 3 halves times a third x cubed. So obviously you can cancel out 3 and 3. You get x cubed divided by 2, and x ranges between 0 to 3. So if you plug in 3, you get 27 over 2. If you plug in 0, you get 0 over 2, which is 0. So the outcome is 27 over 2. Part B, you have the exact function. Your function is x squared y. Now the question changed the order in which you take the integral. Okay, the inside integral is now with respect to x. Your outside integral is with respect to y. So first we take the integral with respect to x, then we move on to y. Integral of x squared y with respect to x is nothing but, let me write the detail for you here, x squared y with respect to x is equal to a third x cubed y. Then we plug in 3, which is 27 divided by 3, or 9y. Now we take the integral with respect to y, because our outside integral has variable y. Now the integral of 9y is equal to 9/2 y squared. First, we plug in 2, then we plug in 1. Here you have 9 times 2 squared over 2 minus 1 squared over 2. So you have 9 times 4 minus 1, 3/2, which is equal to 27 over 2. In this special case, the outcomes of these two integrals are the same. Why is that? The reason is x and y have nothing in common with each other. X squared and y are two separated functions. Frobenius theorem. Very well, we have a nice theorem referring to previous example. If f is a continuous function on a rectangle, the official way that we define a rectangle is the set of all ordered pairs such that your x ranges between a and b, your y ranges between c and d, then the double integral of f over r with respect to two variables x and y is equal to double integral of function f with respect to y, then with respect to x, which is the same as taking the double integral of function f with respect to x, then with respect to y. The outcome must be the same. Let's take a look at another example. Here you have a function x minus 3y squared, and you are taking the double integral over a rectangle. So this rectangle, if you want to visualize this, on x-axis, you are in between 0 and 2. So 1, 2, 3. And your y is between 1 and 2. This is your R. Very nice area in the plane. So based on Frobenius theorem, you can take the integral with respect to x, with respect to y, or with respect to y, then with respect to x. That's totally up to you. Do we have a continuous function? Of course. This is a nice function, a polynomial function in two variables, and it is continuous. Integral of x minus 3y squared with respect to y is equal to xy minus y cubed. So take a look at this. The integral of x minus 3y squared with respect to y is xy minus 3 over 3 y cubed. That's why we can cancel out 3 and 3, and you have xy minus y cubed. Now we plug in 2, then we plug in 1, and we subtract. When you plug in 2, let me write it here for you. 2 for y, you get 2y minus 8. I'm sorry, 2x minus 8 minus, now you plug in 1 for y, x minus 1 dx. Very well, 2x minus x is x. Negative 8 plus 1 is minus 7. Now we take the integral with respect to variable x. The integral of x is x squared over 2 minus the integral of 7 is 7x. Then we plug in 2. If you plug in 0, it doesn't give you anything. The outcome is going to be just 0. So you have 4 over 2 minus 14. 4 over 2 is 2 minus 14, which is negative 12. Again, you can change the order of these two variables and you get exactly the same value. Another example for you. This question says, evaluate the double integral. Perfect. Do we have a nice function? Is the function continuous? Can we apply Fubini's theorem? Perfect. First of all, e raised to x minus y can be written as e to the x times e to minus y. Remember that the integral of e to the x dx is e to the x, and the integral of e to minus y dy is minus e to minus y. Now let us take the integral. The integral of this function with respect to x, with respect to y, or with respect to y, with respect to x can be written this way. 0 to 2 e to the x dx, 0, 3 e to minus y dy. The first integral is e to the x, 0 to 2 times the second integral, negative e to minus y, 0 to 3, which is equal to e squared minus 1 times minus e to negative 3 plus 1. By voiding these two, we get e to negative 1 plus e squared plus e to negative 3 minus 1. So when you have a function in x and y, and x and y's are separated from each other, you can actually separate the integrals. The integral of a to b of x, c to d of y, f of x times f of y dy dx is equal to the integral with respect to x, a to b, f of x dx times the integral c to d, f of y dy. So you can separate the integrals since these two functions are separated from each other. There is no addition, there is no subtraction, just multiplication between these two functions. Next, another example for you. Here you have integral 0 to pi, integral 0 to 3. So the inside integral is with respect to y, the outside integral with respect to just x. So of course you can separate these two. You can write it as the integral 0 to pi over 4 sine x dx times integral 0 to 3 dy. The integral of sine x is negative cosine. Remember that. The derivative of sine is cosine, but the integral of sine is minus cosine. So the first integral is minus cosine x 0 to pi over 4 times, here you have 1. So the integral of dy is equal to y. You get y ranges between 0 to 3. If you plug in pi over 4, you get square root of 2 over 2 or 1 over square root of 2. Minus cosine 0, which is 1, you get 1 minus 1 over square root of 2. And if you calculate y, when it ranges between 0 to 3, the outcome is equal to 3. Next example. Suppose R given as a rectangle 1 to 2 and y ranges between 0 to pi. Okay, 2. So 1, 2, a little bit of up to get to pi. 3. Okay, 1 to 2 and 0 to 3 point something. So this is your R. Our goal is to find the integral of y times sine of x times y dA. Guys, here you cannot separate these two functions because you have y inside sine. So there is no way you can write this as the product of two integrals. Unfortunately, it doesn't work in this case. So here you have two options. Since the function is continuous, you can either say that, hey, I can take the integral 1 to 2 x y sine xy, then take the integral with respect to y, 0 to pi, so dx dy, or you can say that, hey, I want to take the integral with respect to y first, then I want to take the integral with respect to x. One of them has more work to do. Take a look at the second one. Here you are taking the integral with respect to y. It means that you are taking the integral of y times sine of y, which requires more work. So before taking double integral, always check to see which one is easier to work with. We prefer to find the integral in this case. First, we take the integral with respect to x, then we take the integral with respect to y. The integral of y sine xy with respect to x, it means that your y is just a constant. It's like writing it like this: 2 sine 2x dx, which is minus cosine 2x. This integral is similar to the integral of 2 sine 2x, which you already know how to calculate this integral. So the inside integral with respect to x is minus cosine xy, x ranges between 1 to 2 dy. Very well, let us plug in 2, then we plug in 1. When we plug in 2, we get negative cosine 2y minus minus cosine 1 times y, which is y. This integral is equal to the integral of negative cosine 2y, integral of let me just write it here for you. Minus cosine 2y is equal to, you have minus sign, and the integral of cosine, which is your sine. But here you have 2y, so you have to multiply the function by a half 2y. The integral of cosine is nothing but sine. Now you plug in pi for both of them, then you plug in 0 and do the calculation. Next example. Question says, find the volume of the solid like S that is bounded by elliptic paraboloid x squared plus 2y squared plus z equals to 16, and the planes x equals to 2, y equals to 2, and the 3 coordinate planes. Let us take a look at the object here. What are we dealing with? Our function f of x and y, a function in 2 variables, is 16 minus x squared minus 2y squared. So this is your inside function. Now take a look at these 2 planes, x equals to 2 and y is equal to 2. We have another condition that says 3 coordinate planes. So it means that your x is sandwiched between 0 and 2, and your y is sandwiched between 0 and 2. Now we can form our integrals. We have a double integral. Here you have 2 variables, and you have a nice continuous function. It doesn't matter if you take the integral with respect to x, then with respect to y, or with respect to y, then with respect to x, because your function is continuous and a nice function. So you can take the integral, the inside integral with respect to x, which is 16x, minus a third x cubed, minus 2y squared. Note that we are taking the integral with respect to x. So we just add a new variable x. Then we start plugging in 2. Since in all of these cases you have x present, if you plug in 0, the outcome is 0. So the lower bound is not very important. By plugging 2 and simplifying the expression, the outcome is 88 divided by 3 minus 4y squared. Now we take the integral with respect to y. The integral of constant 88 divided by 3 with respect to y is 88 over 3 times y minus the integral of 4y squared is 4/3 y cubed. Now we plug in 2, then we plug in 0, and we calculate the volume. So this is the theorem that I just mentioned for you. If you have two nice continuous functions and they are separated from each other, they are not dependent on each other, you can separate the integrals. For example, if R is a rectangle, 0 to pi over 2, 0 to pi over 2. And the question says, find the double integral sine x cosine y over this plane, this small rectangular plane. Then you can separate these two integrals. Then multiply the outcomes. The integral of sine is minus cosine, then you plug in pi over 2, then you plug in 0. The integral of cosine y is sine y, then you plug in pi over 2, then plug in 0, which is equal to 1 times 1, which is 1. One last example. Okay. Here you have double integrals x, y, e to the y, dA. And your R is, let's see, x and y such that x ranges between 0 to 2 and y ranges between 0 to 1. Very well. Here we have a continuous function, and these variables are not dependent on each other. It means that you can separate the integrals. The double integral is now the product of two integrals. The integral x dx with respect to x, and the integral of y e to the y with respect to y. R is rectangle. This is your R. 0 to 2, 0 to 1. This is the domain on which you are taking the integral. This is your R. So it seems like the domain was dropped, but since I have the solution right here, I know the rectangular domain is all points, x and y, such that x, so here take a look at this variable x. The outer integral is related to variable x. X ranges between 0 to 2. The inside integral is connected to variable y. So y ranges between 0 and 1. Okay, perfect. So one integral is easy. 0 to 1, x dx, which is a half x squared. Then you plug in 0, then you plug in 2. The second integral, you have to use integration by part, 0 to 1, y e to the y, dy, uv minus integral v du. So suppose u is e to the y. Let's use the second format. Okay. So suppose u is so let me show you this one. Suppose u is e to the y and dv is y dy, then du is equal to ey dy, but your v is going to be a half y squared. So it's not a wise choice. Instead of reducing the integral, you're making it more complicated. So suppose your u is equal to y and dv is equal to ey dy. Du is equal to dy and v is the same as ey. Very well. uv minus integral v du. uv y ey minus integral v du. So ey dy. You already know how to take the integral. So here you have y e to the y minus e to the y. Integration by parts. Now here you plug in 0 and 1 and you calculate the second integral. So the first integral is a half 2 squared, which is 4. And the second integral, if you plug in 1, you get e to the 1 minus e to the 1, which is 0, minus, now you plug in 0 for y. The first term is 0, minus e to 0, which is 1. So a half times 4 is 2. 2 times 1 is 2. (15.3). Perfect. Now suppose you want to take the integral over different domains. Last time we talked about a nice rectangular shape like R. Now suppose you're changing that domain into other domains, other shapes. Of course, you learned about polar coordinates before. You can apply polar coordinates change in variables into or double integrals. Your x is r cosine theta and your y is r sine theta. And the dA, dx, dy is equal to r dr d theta. That's how you can use polar coordinates to convert xy into r theta. Be careful, you have to make 3 changes. You convert x into r theta, y into r theta, dx dy to r dr d theta. Let's take a look at one example to see what's going on here. The question says, find double integral x dA, where your domain is the disk with center, the origin, and radius 5. So you are taking the integral over this domain. 5 minus 5 minus 5. Perfect. First of all, we can convert x into r cosine theta. We already know that. Wherever we see r, we can write r times cosine theta. We're converting x into polar format. But what about our domain itself? Our domain is just a circle, a complete circle, and all points inside the circle. So here you have a solid disk. Your theta is ranges between 0 to 2 pi. This is your theta, just rotating the whole. And then your r, your radius, changes between 0 and 5. Perfect. Our double integral can be written as the integral, the inside integral with respect to r, outside integral with respect to theta. Guys, remember that when you're converting dA to r and theta, dA is equal to r dr d theta. Don't forget about your radius r. Perfect. We have integral 0 to 2 pi, 0 to 5, r cosine theta times r dr d theta. Do we have a nice function? Do we have a separable function? Of course. It is equal to integral 0 to 2 pi, integral 0 to 5, r squared cosine theta dr d theta. R and theta are not dependent. So we can write these double integrals into the product of two integrals. The first integral is 0 to 2 pi cosine theta, which is obviously 0. And the integral of 0 to 5 r squared dr, we don't even have to calculate this because we know that the first integral is 0, so the outcome is equal to 0. This extra r is coming from converting your dA into r d theta. So your dA is the very small area. You take a very small area and you convert it into polar format. So this just piece, this sector, this is a very small part of radius, which we denote by dr. So again, this line is the radius of your circle, and you are taking a very small part of it, denoted by, if you remember, delta r or dr, when r is getting very small. But what about this length here? What is this length? Is it just d theta? Of course not. It is r times rate of change in your angle. This length is r d theta. The product of these two is equal to the area, to this small area. Length times width is your area. That's where this r, extra r coming from. Very well. Example. Find the volume of the solid that lies under the paraboloid z equals to x squared plus y squared above xy plane and inside the cylinder x squared plus y squared equals to 2x. Very well. First of all, identify your two variable function. This is your f of x and y. X squared plus y squared. Then start finding the area over which you are taking the integral. Perfect. We know that we have a cylinder. X squared plus y squared equals to 2x. Complete the square to actually identify this using polar coordinates. It's very helpful. So here you have x squared plus y squared minus 2x equal to 0, which is x squared minus 2x plus 1 plus y squared equals to 1. If you group these together, you get x minus 1 squared plus y squared equals to 1 squared. But what is this shape? This is a circle centered at 1 and 0 with radius 1. This is your shape here. X and y. Perfect. So for this shape, as you can see, your theta ranges between negative pi halves and pi halves, only on this side. So for sure you can say that, hey, my theta is between minus pi halves and pi halves. Then we have to think about r. R is not 1. Guys, be careful here. R ranges between 0 to these points on the circle. This is your R. So R ranges between 0 and this, let's say, curve. But how do we find this curve? We can plug in R equals to, X equals to R cosine theta and Y equals to R sine theta. Okay, by plug in those, it's not 2, it's not 2. It's 0 here, this is your R. R ranges between these. It's not a fixed number, it's a function. So you know that you have x squared plus y squared equals to r squared. X is r cosine theta, y is r sine theta. So your r squared is equal to 2r cosine theta. That's how we define equation of a circle. X squared plus y squared is equal to r squared, and x is equal to r cosine theta. So your r squared is equal to 2r cosine theta, or r is equal to 2 cosine theta. This graph, this curve here is r cosine theta. So your r is changing between 0 to r cosine theta. 0 to r cosine theta. R ranges between 0 to r to 2 cosine theta. Okay, now that we have all the information we need, we can start solving this volume problem. First of all, our function, our two variable function is x squared plus y squared. Now, x squared plus y squared converting into polar coordinates is nothing but r squared. My dA is equal to r, dr d theta. My r ranges between 0 to 2 cosine theta, and my theta ranges between negative pi over 2 and pi over 2. By multiplying r squared and r, you get r cubed. The integral is a fourth, r to the 4, and your r ranges between 0 to 2 cosine theta. We plug in 2 cosine theta. We get 16 cosine 4 divided by 4. 16 divided by 4 is 4. So you write 4 outside the integral. The integral of cosine to the 4th d theta, if you remember your integrals from Math 1b, we can rewrite cosine to the 4th as cosine squared squared and cosine squared. So let me write it here for you. Cosine squared is equal to 1 plus cosine 2 theta divided by 2. And since you have cosine to the 4th, you have to raise it to the 2nd power as well. Now, we just multiply 1 plus 2 cosine 2 theta by itself and 2 by 2, which is a 4th. 8 divided by 4 is 2, and by multiplying 1 plus cosine 2 theta by itself, you get 1 plus 2 cosine 2 theta plus a half 1 plus cosine 4 theta. Now we have functions, nice functions that we know how to take the integral. The integral of 1 with respect to theta is theta. The integral of 2 cosine 2 theta is 2 divided by 2 sine 2 theta. Then a half theta plus a half times a 4th, which is 1 over 8 sine 4 theta. Your theta ranges between 0 to pi halves. After plugging pi over 2 into the function, you don't have to worry about theta here equal to 0, because if you plug in 0, 0, 0, the outcome is 0. So forget about the second or lower boundary, just plug in pi over 2, and the outcome is 3 pi halves. Perfect. This is our crazy, beautiful object. Very well. Let us talk about surface area. First of all, from previous calculus lectures that you learned, we defined length to be the sum of smaller line segments, which are straight lines. So to define any curves, we can just use small, very small line segments, add them all together, then take the limit, send the limit to infinity, and have the length of a curve. We're going to use this idea to find the volume over crazy looking domains. So these are the algebra behind this. To define a surface area for a function, you have to just cut these into very small, very miscellaneous rectangular shape. If you add them all together, then you actually form the surface. The surface area is defined as double integral of square root of partial derivative of f with respect to x, then you raise it to 2, plus partial derivative of f with respect to y, you raise it to 2, plus 1 times dA. Again, your dA is either dx, dy, or your dA is dy, dx. That's how we define surface area. Remember that f of x is nothing but partial derivative of z with respect to x, and f sub y is partial derivative of z with respect to y. What is z? Z is your function in two variables, x and y. Let's take a look at one example to feel more comfortable about this. Example says, find the area of the part of paraboloid. So here you have your function in two variables that lies under the plane z equals to 9. We want to find the area of the part. So we're actually looking for the surface area. We just learned about a nice function about surface area. Double integrals, square root of 1 plus partial derivative of f with respect to x squared plus partial derivative of f with respect to y squared and dA. Perfect. So, taking partial derivatives is easy. You are taking the derivative with respect to x, you get 2x. So partial derivative of z with respect to x is 2x. Partial derivative of z with respect to y is 2y. Nothing important here. How about the domain? I only know that my plane is z equals to 9. How can I find the boundaries for x, for y? So let us set these equal to each other. I know z is equal to x squared plus y squared. At the same time, I know z is equal to 9. So if I find the intersection between them, I can actually find that domain. So by setting x squared plus y squared equals to 9, you actually get a complete solid circle with radius 3. Your theta is between 0 to 2 pi, and your r, as you can see, is between 0 to 3. And again, remember that dA is now r dr d theta. One plus 2x squared plus 2y squared is 1 plus 4x squared plus y squared. X squared plus y squared is equal to r squared. Guys, you cannot use 3 or 9 here. You have to use your variable. So your surface area is equal to the integral 0 to 2 pi. This is your outside integral. And the inside integral 0 to 3 of square root of 1 plus 4r squared r dr d theta. Perfect. Can I separate these two integrals? Of course. I only have r and d theta. There is no theta here. So I know that my angle ranges between 0 to 2 pi. And the second integral is 1 over 8 square root of 1 plus 4r squared, 8 r dr. So why I need that? Take a look at this. The integral of 1 plus 4r squared r dr. First of all, by substitution, your u is equal to 1 plus 4r squared. Du is equal to 8r dr. So r dr is missing 1/8. You multiply your integral by 1/8 and 8. So here you have 1/8 integral u du. And this is inside the bracket. Now this integral is equal to 1/8. This is u½ so let me write the whole thing for you. u², du, which is 1/8 times 1/1 plus a half, u²1 plus a half, which is 1/8 times 2/3, u2 3/2. This guy is coming from this calculation. So as you can see, we are dealing with a lot of techniques that we learned in Math 1A. Please review those techniques. After that is just pure algebra. You plug in 3, you plug in 0, you simplify the whole thing, and actually the outcome is pi/6 37 times square root of 37 minus 1. Guys, any question here? Okay. Last example. Find the surface area of the part of the surface. Very well, we have our function, two variables function that lies above the triangular region T in xy plane with vertices 0, 0, 1, 0, and 1, 1. So we have our function f of x and y. Taking partial derivatives, easy. Two x, just 2. What is our goal? Our goal is to find our region, T. So to find the region, you have to use algebra, intermediate algebra, and to write equation of the lines. So your x is ranges between 0 to 1. This is my x. My y is ranges between, so your y is changing between 0 to line x. So your y is a variable. X is between 0 to 1, and y is between 0 and x. So your double integral is your inside integral. Y depends on x. It must be inside. Then the outside integral is taking the integral with respect to x. Guys, you cannot switch these two. Very well. So the integral of 4x squared plus 5, you can actually take this and write it outside the integral. So this is the integral 0 to 1, square root of 4x squared plus 5, integral of dy 0 to x dx. So this integral is just saying that you are taking the integral 0 to x of dy, which is y ranges between 0 to x. This x is coming from taking the integral with respect to y. So now you have the integral with respect to x of x square root of 4x squared plus 5. By using substitution, u is 4x squared plus 5, so du is 8x dx. 8 is missing here, so you multiply and divide by 8. So we have, let me write down the detail for you. I don't want to miss out anything. So here you have integral 0 to 1, 1 over 8, 8x square root of 4x squared plus 5 dx, which is 1 over 8. The integral square root of u du, which is 1 over 8 times 1 over 1 plus a half u2 1 plus a half, which is equal to 1 over 8 3 halves times u2 3 halves. This is, the whole thing is coming from this substitution and doing the algebra. Then you plug in 1, you plug in 0, and you find the surface area, which is 1 over 12, 27 minus 5 square root of 5.